Adding vectors algebraically. Welcome to 2D kinematics. When you add vectors we've learned already how to add vectors by drawing them out. And now we're going to learn how to do it algebraically. It's also going to involve some trig. So drawing scale diagrams for each problem is not a great use of your time. Physicists prefer to be more efficient. We will still draw vectors and directions accurately, but we have a better way of finding the resultant vector. Let's explore a few ways math can help us once again in 3 different situations. So if you have perpendicular vectors, here we have, one vector here and one vector here. The resultant vector for here would be drawn like this. And this is like probably the simplest one because we have a right triangle. And so you can use the Pythagorean theorem. Here, if you have non-perpendicular vectors, you can't use Pythagorean theorem, but you can use other methods such as ln sines and cosines. And then here, obviously, this is not a triangle because there's multiple ones. And so if you have 3 or more vectors, there's other ways to do it. If 2 vectors are to be added together and the directions are perpendicular, you draw the vector addition, then use the Pythagorean theorem and trigonometric ratios to find the resultant vector. Remember that the resultant vector must include both magnitude and direction. For example, Neil walks 1,500 meters north. I'm just going to draw a little diagram as we go. Oopsie. Neil walks 1,500 meters north, then 750 meters west. And this is obviously just approximated. Find this total displacement, including direction, of course. So the resultant vector would look something like this. Oopsie. I should have drawn this, excuse me. I did that incorrectly. Because he didn't walk back to the beginning, he then walked like this. So the resultant vector would then be like this. Okay? So you can see here we have 1,500 meters north, 750 meters west, and we're looking for the resultant vector here. We know that a squared plus b squared, we can say that this is a, this is b, and this is c. A squared plus b squared equals c squared, right? So this would be our c squared, this is our a squared, and this is our b squared. When we plug in the numbers, we can solve and we get that the answer is 1,677 meters. Okay, now what's the angle? To find the angle, we can use our SOHCAHTOA, right? We have opposite and adjacent. So if we look at our SOHCAHTOA, we have these two. So we're going to use this. So therefore we have tangent of theta equals opposite, which is our 750, over adjacent, which is our 1,500. And if you put that into your calculator, you'll find that it's 26.6. So now you see your math coming to life. You see, oh, why did we learn these trigonometric functions? Well, here's one of the uses. When you add non-particular vectors, you will notice that the 3 vectors, that are not particular, draw the vector addition with the angles labeled, then draw the resultant. You'll notice that the 3 vectors form a triangle. Since the original 2 vectors are not perpendicular, you cannot use the Pythagorean theorem. Instead, you use the cosine law and sine law to solve for the missing magnitude and direction of the resultant vector. You may need to use some angle rules from math class, including the sum of angles in a triangle is 180. So just basic geometry you're going to need to solve for these kind of problems. Here's example 2. Erwin carries his cat around for a walk. Erwin walks 25 meters west, 25 meters west, 15 degrees north, then 110 meters south, 40 degrees east. Find Erwin's total displacement. So here we have Erwin walked 15 degrees west, 15 degrees north. Okay, so that would be here. 15 degrees, oopsie, that's not a highlighter. 15 degrees west, north, right? And then he walked after that, he walked south 40 degrees east. So here's south 40 degrees east. So he goes like this, and then he went like this, right? So the green is our resultant vector. So this right here is our resultant vector. So how would we solve for that? So we know that this right here is 15 degrees, like that. And we know that, so therefore we know that this is 15 degrees, right? Maybe I need a smaller pen. Let me try that. Because this line is parallel to this line, so therefore these are opposite interior angles, I think that's what it's called. So that's 15 degrees. And if this is 40 degrees here, then we can calculate what theta is. So we know that 90 minus 40 minus 15 is going to be theta. 90 minus 40 is 50, 50 minus 15. So our theta should be 35 if I did my math correctly. Okay, so we can do things like that. So see, now we solve for theta, which is 35 degrees. And then now we can do our law of sines and cosines and whatnot. So here, we're not going to use this a whole lot, so I'm not going to focus on this a whole lot because these are more complex problems, but I did want you to understand that the law of sines and cosines that you learned in pre-calc or in trig is useful. Okay, so this is continuing with that example. If you'd like to, go ahead and work through that on your own. When you add 3 or more vectors, you need to do a new strategy. So the new strategy is that you break each vector into its horizontal and vertical components. So for example, this is just telling you the math. Let's see if we can go to an example. Well, I'll just draw an example. In this method, so let's say you have, now our line is not thick enough. Let's say you have this vector, and then we'll change colors. And then you have like this vector here. And then you have, let's see, I want that to be this vector here. What you can do is for each of the vectors, you can break it into its different components. So if we just focused on this one, it has an x component and a y component that adds up to the resultant vector. That's kind of hard to see because it's yellow. So I'll change that to orange. But you can see, that we can draw horizontal and vertical. Instead of taking 2 vectors and adding them up to the resultant vector, you can take the resultant vector and decompose it, break it down into 2 vectors that add up to that. And so that's what we do here. Here we have we can say this is vector A, and here we have A sub x, because it's like the horizontal one, and A sub y. And if we add A sub x plus A sub y, we get the resultant vector A. And you can do that for each of these vectors. So you could do that for the red vector and the blue vector, okay? This requires the use of basic trigonometric ratios. You know all these, SOHCAHTOA already. Each vector is like the hypotenuse of a right-angled triangle. It can be written as the sum of a horizontal vector and a vertical vector. Each vector is broken down into a horizontal component, also called the x component, and a vertical component, the y component. The components of the vectors receive a subscript in their name. So delta D1 has horizontal component delta D1x and vertical component delta D1y. V3 has horizontal component V3x and vertical component V3y. Find the horizontal and vertical components of each vector. So we have 75 meters per second, north 36 degrees east, and this one. So let's go on to the next page. So here we have our vector, and we're going to break it into the Vx and Vy components. Okay, so we know that, and since this is 36 degrees, and we know our age, right? So if we look at our, Katoa, what do we know? We know our h, right? We know our h's, and we know our angles, right? And so if we are trying to solve for Vx, we can do, Vx is opposite from 36, right? So that's this one. So we could do sine of 36 is equal to Vx over 75, right? So we have that. We can put that in place. Here we have sine 36 is Vx over V. So then you solve and you get Vx is 44.08. You could do a similar thing for Vy, but now Vy is actually adjacent to 36, not opposite. So you're going to use cosine. We'll do that on the next page. So here cosine is equal to adjacent over hypotenuse. Cosine 36 is Vy over V. Put that into the equation and you get Vy is 44. So you can see that they're both 44. That's kind of unusual. That doesn't seem correct. So I'm going to check the math on that. Let's pause the video for a second or just stay tuned. So if you do 36 cosine 75, let's see, 36 cosine times 75. Okay, yeah, the math on this one was wrong. This is actually supposed to be 60.67 meters per second north. Okay, and I'll double check the math on the other one since there was obviously a mistake on this. But the other one, this one is correct, but the Vy should be 60.67. Okay, example 3, here's another one. This is the one that's 4.3. Here's our resultant vector. We break it into x and y components. And so here, if we're looking for this one, it would be cosine of 18 degrees is equal to adjacent, which is our delta dy, over delta d. And they already kind of solved to get for delta dy, you would multiply both sides by delta d, and that's where you get this equation. Then you put in your 4.3, and you get a 4.09. So here, and then on the next page, we're going to use sine. Very similar. Here we have sine of 18 degrees is going to be our opposite, delta dx over delta d. When we multiply both sides by delta d, you get this equation. You plug in place, and you get that to be 1.33 kilometers west. So you can break it into the x and y. It is easy to add all the horizontal components together and then add all the vertical components together. So if you have, if we go back to our example up here where I drew the three different, if we break this into their x and y components, let me choose different colors. So here, if we break this into its x and y component, and we can say that this is vector b. So then this is going to be bx and b sub y. And then here we can break this into its x and y components. And we can have here, if this is c, vector c, this is vector c, this could be vector cx, and vector cy. So if we wanted to know the resultant vector, we know that the x component of the resultant vector is going to be, we can say the resultant vector is d. Okay, so if we wanted to know the horizontal component of the resultant vector, it's going to be just all the horizontal components added up. And if we wanted to know the vertical component of the resultant vector, that's just going to be all of, the vertical components added up. Okay, so I'm going to erase all this because I want to show that graphically. So here, it started over here, oopsie, it started here, and it ended here. So if I were to draw the resultant vector, it would look like this. Okay, and so then if we were to, if we were to copy that, like it looks something like this. And we break it into its components, then this would be a sub x plus b sub x plus c sub x. That's how long that component would be. Does that make sense? And this would be a sub y plus b sub y plus c sub y. Then you could use Pythagorean theorem to find what the resultant vector is. A lot of math, but that's how you would do it. Let me scroll back to where we were. So this is what we were talking about here. It's easy to add all the horizontal components together, then add all the vertical components together, like that, okay? This provides the resultant vector's horizontal and vertical components, and the resultant vector can then be found using Pythagorean theorem and trig ratios. So adding vectors algebraically, a horse in a pasture travels 55 meters west, then 25 meters south, then 67 meters south, 17 degrees west, then 13 meters north, 33 degrees east, and finally 24 meters north, 29 degrees west. Find the horse's total displacement using the component method. So here, the first two are really easy because they were just west and south. So the horizontal component for the first one is just negative 55 meters, because we're going to say that east is positive. So this would be negative 55. And the vertical component, there was no vertical component. So then for the 25 meters south, there's no horizontal component, and south is in the negative direction, so that's negative 25. Then for the third component, we have 67 meters south, 17 degrees west. So here's the resultant vector, right? And we're going to use our sign, SOHCAHTOA, right? So we find that the y component is 67 meters cosine 17 degrees, and this is 67 meters sine 17 degrees. And so if you put that into your calculator, you can see that in the horizontal direction, it's going west, so it's going to be negative. It's negative 19.59, and it's going again negative because it's going south, 64.07 meters. The next one is, this is the resultant vector. And so here we have 13 meters sine 33 and 13 meters cosine 33. You plug that in. Now we're going east and north, which are positive, so we have 7.08 and 10.9. Here, this is the resultant vector, and here are the components. Now on this one, it's going negative in the horizontal direction, but positive in the vertical direction. Now you have all the components, and you add all those up to get negative 79.15 meters. So it's going west 79.15 meters. And in the vertical direction, you add all these up, and you get negative 57.18. So it's going south 57.18 meters. So now you can put those together, west and south. So it's going this way, and you can get the resultant vector. So here we have, this could be our A, this could be our C, B, and this could be our C. So we have 79.15 meters squared plus 57.18 meters squared equals C squared. You do the math on that and take the square root, and you're going to get 97.64. Now you have to find the angle. To find the angle, you know the opposite and the adjacent, so you're going to use tan function. You plug that in, and you find the inverse tangent to get the 35.8 degrees. So that's your answer. It's, is this still going on? Yeah, so the final displacement of the horse is 98 meters west, 36 degrees south. A lot of work to find that, but we did it. Any questions?